it's going to look like this. When we draw it in the line angle drawing, it's going to look like this. And in this line angle drawing, again, that was the beginning of this morning, talking about having a double bond that is tri-substituted, right? So the double bond is tri-substituted, it's regioselective. So when we do BH3 in THF, I think everybody remembers that BH3 and THF, it was going to do the non-Markovnikov or anti-Markovnikov. The book called it anti-Markovnikov. I hate calling things anti-Markovnikov. I like to call it non, because anti, of course, your stereochemistry outcome. So when we look at it, it's a really good idea to go ahead and put the hydrogens so that you can tell them apart. We know that this time the alcohol will go there. So we're going to go ahead and put the OH is going to go there. The hydrogen also goes in a syn stereochemistry. So this is seen as a syn stereochemistry. Syn stereochemistry when both groups are coming from the same side. And if I have 1, 2, 3, 4, 5, 6, 7, 8, 9, and you're 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, so there's your alcohol. Again, the alcohol can either be chiral, so both from the top or from the bottom. Okay, is everybody okay with that one? Okay, we look at number 9. And number 9, it looks to be 1, 2, 3, 4, 5, 6. So this will be 6. And on 1, 2, you have the double bond. And there's the methyl right there. Again, all right. Again, this one is tri-substituted. This PC, somebody said we don't know what this is. This pH, CO3H, that number there, 3. Okay, that stands for a peroxy acid. The most common peroxy acid was MCPBA. Did you remember hearing this in Chem 3? MCPBA is the most commonly used peroxybenzoic acid. And what this does is you end up generating an epoxide, and your epoxide here will continue. And I saw many of you drawing this like so, and that is correct. So many of you drew it like that. Yes, it happens in syn stereochemistry, so you could have drawn them with wedges. I'm not very, when we're reviewing like we are reviewing now reactions, I'm not very sticky glue about the drawing, because my big focus here is to bring in a lot of information back. Do you know how to name these guys? Our class did learn how to name those. People from Chem 3, anybody remembers how we named that? I know your teacher. All right, so we had to find the longest continuous chain again. So it went like that. Okay, so we saw that it was 1, 2, 3, 4, 5, 6. Okay, and then we call that an epoxy. So on 2, 3, this was called epoxy. And then on 3, we had the methyl, and all of that is called hexane. So they are called epoxy. Esters are not parents. They really are not parents. They are substituents all the time. And so as a substituent, the 3-member ring was an epoxide. The compounds are called epoxide. Common name is epoxide. Like this guy, this is called an epoxide. If those were all hydrogens, this is called an epoxide. So now that you're attaching it onto a bigger chain, it's going to be given a substituent, and as the substituent is an epoxy. And all you have to number is the carbons, where you will find that epoxy. But the epoxy is really the triangle with the O. So it appears on carbons 2 and 3. There is a subsequent reaction, and the subsequent reaction is to open it up in acid. I don't know if you saw that the second step is to open this up. So you can open an epoxide in presence of acid, and that opening of the epoxide in presence of acid is going to lead to the diol, but the diol is going to be in an anti-stereochemistry, meaning 180 degrees from one another. So when we open it up, this one's much easier to draw. When we're going to go ahead and open this up, I can easily put an OH to the top and an OH to the bottom, and then it makes sense that that methyl goes to the top like this. That's one way of doing it. I'm sure not the best way of doing it, but that's one of the ways of doing it, where you have the OHs going in that anti. In reality, if you really want to draw anti correctly, that is not the way it's done. Drawing anti correctly is like this, where the OHs are shown as 180 from one another, and then you have an atom to the front and to the back, and then you would have to add all those pieces. This is the real way of drawing anti. All right, again, we're just going quick and sloppy, but if they said draw perfectly, that's how an anti is drawn perfectly, okay? All right, and the very last one, which is number 10. Oh, do we have to name it? Sorry. If we're naming it, I'll add all the pieces. Come on. We're adding all the pieces. This guy can either have a hydrogen to the back and a methyl here. This can have a methyl here and a propyl to this. Okay, I'm making stuff up. Is everybody there? So that looks like that there. If we're naming this guy, how are we going to name it? 3-methyl. Okay, and then? Very good. Hexane, 2,3-diol. Very good. Like that. Okay, and the very last one, which is 2,2,4,3-methyl on that page. So number 10, we're going to look at it like so. So 1, 2, 3. There's the hexene on 3, and on carbons 2 we have that. 2, 3, and 4 we have that. So those are all of them. And now we're going to go ahead and add the mercuric acetate. Mercuric acetate is your oxymercuration. If the solvent is water, like it is here, if the solvent is water, it's going to produce an alcohol. Okay? If the solvent was an alcohol, it's going to produce an ether. So let's take a look at both variations. First thing that happens is the formation of an organomercurial alcohol. I'm sure Dr. Anais even said to all of you, we're not interested in that. We're interested in the end, and the end is this sodium borohydride, where you're going to go ahead and reduce the carbon. You take the mercury off, and in its place you're putting in hydrogen. So say we're reducing the carbon. All right. At the end of all of this, what we have is a Markovnikov alcohol. So if you're looking at the alkene has regio selectivity. So at the end of all of this, if we draw it correctly, you stay the way you were. And over here, I'm going to put that guy and the OH to the bottom. You don't have to draw it like I did, but the carbon that had that methyl, the carbon that has the methyl is the carbon that gets the OH. Okay, we have to name it. Now we start numbering from here, and it becomes your 3, 4, 5. So it's now the number changes. We're coming from the end, so this will be 1, 2, 3, 4, 5, 6. So 3, 5, 5, trimethyl, and then hexane, 3-ol. So let's keep the same alkene that we started out with, keeping the same alkene that we started out with. And now let's go ahead and in its place use alcohol for a solvent. So let's use ethanol as the solvent and then see what's going to happen. When we use ethanol as the solvent, instead of making an alcohol, we're forming an instead of the alcohol, you're forming an ether. And so everything would look exactly the same way. Everything looks exactly the same way. The only difference here is the alcohol will go ahead and make an ether. So it looks like that. It's like you lost that hydrogen. You're forming an ether. Does everybody remember how to name that one? Ethoxy is correct. So ethoxy is correct. So the way that that one will be called will be 3-ethoxy. And then the same thing, 3, 5, 5, trimethyl hex. Same. Trimethyl hexane. The alkane is now the parent. Okay, so alkane is the parent. Alphabetically again. So the E for ethoxy and the methyl. Okay, we're gonna do number 2. And what I would like to do with number 2 is this. So the only thing you need to do, and hopefully everybody can do this, you don't have to keep repeating. So I think everybody knows that this will be the 2-methylpentene, 1-pentene, so you don't have to keep drawing it, right? You don't have to keep drawing it. So all you want to do is you're just going to put A and draw, B and draw, C and draw. So we're doing A through Q, A through Q.
What?
CO2 and CCl4. Remember that? That's just a
What number what?
G.
Oh. Good fun.
What did it for E?
Oh, it's fine.
Barely.
What did it for I?
Let me just, yeah, what is that?
It's the W writing.
Dilute?
Remember when it goes like that?
Halohydrin? No.
No. Yeah.
Oh, halogenation.
So.
Are they anti?
Yeah, they're anti. And plus an antrim.
If chiral. If
No, well, we always have plus an antrim because it could go in like that direction or it could be.
it's right there. I put if chiral.
Because remember telling us if it can go in this direction, but it can also switch.
Oh, I don't know.
Something like that.
I think for this one it isn't an answer.
Oh, I didn't even write it for others. I just dropped
Since
MCPBA. Oh, what does that do?
That's the proxy acid.
What's CH2Cl2?
And that was Rado. Oh, CH2CO2.
Where's
That's
the
in
N?
that's in the ethers.
It's not on this one.
It's in ethers.
It won't be on this one. The alkenes, so
Only the acid catalyzed on it. That's what. This is okay in water, in alcohol, in acid, base. The base catalyzed one. And then hydrohydrolytic acid.
is it in there or not?
CH2CO. Wait, is that a base? No, that's not a base. I don't know. Which one is it? I'm not sure. Or maybe that's just. That one.
She does. Second. It's the last one.
Yeah, that doesn't.
It wasn't when you were. The one here? The one right here?
I don't know this one.
That says right on acid.
Oh gosh. Osmodium. What does that do?
The sundial. Right? The OSO4.
What'd you get for?
That's the sundial.
Can I just go?
It's like that and potassium and manganese coal. Those two.
And what?
Yeah, I got a question about that.
I don't know H. I'm just
I
gonna.
don't know what the CO2
What's the E?
I put makes an alcohol.
The most stable one,
I put maconic.
Macan.
Maconic.
Everyone says she's
With the veg, I know, man.
O3, the Z, and acetic acid.
I guess you could.
Oh, well, no, it's A5 really.
No, it's achiral. What does the O3 do? The O.
It breaks up.
It breaks the bond.
It makes what though?
cleavage.
Oh, ketone and aldehyde.
But it's O3 and acetic acid. Oh, yeah. So that's going to make do you remember?
It makes,
Acetic acid.
it makes CO2.
I'm used to like the
It makes
aldehyde.
CO2 and
Wait, what does acetic acid look like?
That's what I'm looking at.
Yeah, I don't know about that. So I said you break up the bond.
Alright, let's Google this.
And then you
never mind.
What is this
50.
acetic acid?
You cut it in half, right? Right?
It won't do anything.
No, but you cut it in half, right? The double bond,
So you can have that CO2.
Oh, you cut it in half. Yeah, it's the cleavage.
right? So you
So
yeah.
break it up into two, like that. And then
Okay, I messed up.
Honestly, you should just take the top two.
oh, maybe it's all in zinc.
Shoot, I messed up.
Oh, I guess it doesn't matter because this one is zinc and the mercuric acid, right, or something like that.
What? Oh, it should still work. I think it should still work. And then
So you would just make a ketone and an aldehyde?
wait, I'm good. Oh yeah, you're right.
Because that's a
You're right.
ketone. When you split up, the first part is a ketone and the other one,
Cool. Yeah, so the other one would be a
but the other one's an
aldehyde.
aldehyde. The other one is just two hydrogens.
So some of you
Isn't
are
that formaldehyde?
questioning some
It's a
of the
formaldehyde.
reagents. For people that are questioning the reagents for H, which is the NCPDA that you're used to
Right.
seeing, the
That's the
CHCl2 is the solvent.
It's
You
cool. It's
just
still
don't
it's still an
open it
aldehyde.
up, okay? The osmium tetroxide was almost always with hydrogen peroxide followed. Other books use this H2S, but you can see it that this would still be the same H2O2.
Oh no,
All right, and then that is HGOAC. That's acetate also. So I think those are the only. You're not doing number 3, so you don't have to worry about number 3, and we're doing number 4, and then we're leaving. Chaos always.
what's
What number am I on? Oh, barely. Okay.
I know the NaH4, but is that the OAC part of it? Like I'm confused.
Where is that?
What
Why am I recording this?